Hi guys, I'm just going to wait and see if anyone else comes into the room. If you are on YouTube, you should be able to say something. So if someone can say whether they can hear me, that would be great. Anyone hear me? I think I'm on this microphone. Hello, is that louder? Sorry if that burst your ears. Okay, excellent, okay. Okay, just give some people a chance to come into the room. I'm just going to queue a few things up in another window here. Hopefully I can share those with you. Hello. Right. Thanks for joining me. I'll start very soon. What do I want? This. Oh, God, I love them. Okay, guys, sorry for the delay. Okay, I'm going to try sharing a window just to test that. It's a while since I've used Hangout on Air. Okay, manage, what can I do? Let's share. Can I do something? Okay, I don't want that. So it has an option to do a screenshot. Maybe we can do that. Okay, we nearly got 10 people in the room. Hi, Chris. Okay. Well, I want you to go and have a look at this part of this video. Just the still frame. I'll put it into the comments because I'm going to refer to it later. And also, where is it? This part is part of the same video. So there's 2 frames on the same video, which you can look at. Now I will refer to this later. Okay, so there has been quite a lot of interest in the vacuum capacitor, and I reached out to Freel.tech and Michael Ergang, who is one of the directors there and an early investor in the technology to take it forward. He came back to me. In fact, he came back to me very quickly, but whatever reason, it got caught in my email and I missed it. But fortunately, Ryan Hunt, co-director of the MFMP, contacted him again, and then he contacted us both back. And so we got some conversation going, and we had a group meeting yesterday to discuss the technology for which he is part of the team. To give you an overview, it was, if you may or may not know it, it's essentially a technology that is claiming to take advantage of the work of Ken Shoulders in condensed electrons in these things called exotic vacuum objects. And it was developed by a Russian guy in the early 2000s. And it secured a few patents, and Michael and his colleagues came along and formed Freel.tech and the sort of commercialization entity in 2015. Michael described himself, and there is some description of what his experience on the Freel.tech website. However, he described himself as working in nuclear energy and working with French and Russian cooperation. In France and Russia are some of the leaders in the world in nuclear technology, as you may or may not be aware. And he's worked in Russia for around about 2 decades. And so he reached out to us from there, and he has the ability to connect in with Russian bodies that he says are much more willing to test novel technologies than perhaps other countries are. And I will have to say that having had dealings with Russian scientists who are very independent-minded, but they're willing to explore ideas based on observation rather than on what someone says is possible. And so he says that, I was describing at one point in our conversation our visit to Roisin Amaza last year, and saying that one of the aims of the project right now, my personal aims in the project rather, is to look at ways to deal with radioactive waste and harmful radioactive nuclides, and the fact that Amaza gas is one potential candidate. Now, he wanted to verify and something that might have been suggested, and he said that they don't claim to have reached 1 kilowatt hours now, but they have reached about 10 years ago 300 watts, and that was actually before the formation of the current entity. And like many technologies that are on the bleeding edge, he explained that they have had reproducibility challenges. Sometimes they work, sometimes they've not worked as expected, and sometimes they've had them work multiple times in a row. So what they've been focusing on over the last couple of years, and it's clearly set out on their website, is to kind of get more reliable technology and test that and so forth. So they do intend to do third-party verification when they are ready, and this was obviously part of the conversation. And the idea of people verifying something out there, you would imagine that they're in, and I will talk about this later, that they're at a point in their development where that kind of concept may or may not work in their favor, but they don't know whether it would, and so they would have to be convinced of that would work in their favor. But of course they do intend to have third-party verification on some point. They are in a position now where they have double-digit of shareholders, and apparently in the third quarter there will be a meeting of a large international group with them, and that's with an aim of scaling up the research in France in a new well-equipped lab. The negotiation for that is sensitive, and they don't want to cause issues because this group is obviously the Freel.tech is a commercial group. The organization that they're working with is a commercial group, and they don't want to cause issues because this group obviously wants to explore the technology to produce devices for use in their own applications for their own commercial avenues. Therefore, they're understandably reticent to potentially risk by kind of like jumping the gun and doing something where they already have a kind of agreement with them about the way that they're going to proceed. And so they don't want to necessarily risk that and just do things step by step and progress cautiously. And this is what you might expect with that. They apparently said that they had a lot of interest from the MFMP video that I had the pleasure of producing on the technology, and they had a lot of contact from a number of countries and so forth. They did say that these 6D6A lamps were, early prototypes, but they're really not the best way to do it. The pattern is not so much about the charging process or this particular device, which was just a test in the early stages. It was really there to protect the basic construction of the vacuum capacitor, so not a particular embodiment. So, the fact that you have an isolated vacuum and cathode, whether it's a thermionic emission or a cold cathode, and then around the outer insulator, you have the anode placed. So he was quite clear to make that point to me. He did mention at one point that there was a certain algorithm for the charge, and this is because of his French origins. It probably wasn't algorithm per se, but formula. It's kind of like a slight mistranslation, I guess. And this may vary, of course, depending on the device embodiment. And so, as I say, that's not the focus of the patent. Anyway. So they were very pleased with the fact that the 300 watt-hour device was less than 40 grams. So I really did my best to push to get some sort of indication as to what might be driving it. He was clear that that was technical knowledge, so, if you manage to chance upon it, then that's great. But that isn't the focus of the patent. The patent is whatever you get it to do to get it working. It's the structure of the thing that is able to store the charge. So I said, well, look, there's people in the community, they are attempting replication, and, sooner or later they're gonna want to know how this works, and I'll go on to explain that I kind of suggested that most of the ways these things work is with a high DIDT pulse charging, or they have radio frequency, or with a DC bias, and he said that. The best results that they had achieved were with DC, but with nuances. And I thought, okay, well, what are the nuances? And he suggested that the best results that they've had recently, and I kind of was like I say, I was working to get him to. If he's saying that the patent is really focused on the physical arrangement of the embodiment. Then it doesn't matter if someone replicates the charging mechanism. They're still blocked by the patent on the way the energy is stored in the physical arrangement. So it's not that important. Anyway, he did at that point say that the latest prototypes, they worked with voltages up to 25 kilovolts, but that again is not very specific. Anyway, and when it was discharging, they were using a 250 kilo ohm resistor. Now, they did express that they had a concern about perception of their product being linked to low-energy nuclear reactions, although he's open-minded about that, and he shared a website, which I will share with the community. He's concerned because you know, there are obviously people in the energy field that, and we all know this, that don't believe low-energy nuclear reactions are possible, even though it goes on in their bodies every day of the week in the form of potassium-40 and carbon-14 decays. But you know, they're saying that whilst nature does it anyway, it's not something that they're aware of, and that's probably because they've not read this book, Space, Earth, Human. Anyway, we're going to talk about that in a second, and how the understanding of how these devices may well be working can be gleaned from that and other reference points, one of which I shared is, and you might like to go and look at the 2 slides that I've pointed to in those YouTube links that I've got in the discussion there. Anyway, so yeah, so he said that if we were to kind of like have a more sensible collaboration with them, that you know, there would have to be some understanding of how the organization that he is connecting with and his investors and him could benefit and so on, and that he would have to be able to have some sort of justification to those parties and those stakeholders that it was going to be in their interest. So, for instance, they could spend the money and go to a lab and get them to do the verification and have the yes, we verified it. And we've been down this road before. I didn't mention this at the time, but it's as an aside, it's about a credibility thing. You know. If you are paying the SEC to verify your mortgage-backed securities, why would the SEC, who's getting money for doing that, not verify your mortgage-backed securities? Doesn't mean the mortgage-backed securities necessarily are good, but your SEC might be saying they're good because they get funded by you paying them to verify the mortgages. So there's always this question where a claimant of a radical new technology goes to a independent lab, but then pays them to do the verification. Now, they might trust this lab. They might have worked with the lab before. If they've got a pre-existing relationship, then that, again, it brings into question the credibility of the data. Now, you could argue that, you know, if this big organization, which we don't know the name of, and you know, in the past, some people have claimed big organizations getting involved with them, but it really hasn't turned out to be the case. You know, you don't want to be ending up in a situation where there's a game going on. And I'm sure that the technology can be realized in the way it's described, but that's because I'm living and breathing exotic vacuum objects ever since I realized that they seem to have signatures in many of the LENR experiments that have been observed today. So it's less of a problem to try and get me to understand that this particular embodiment could be working. But anyway, so there's this concern about low-energy nuclear reactions tainting their product. And so they would have to show some sort of beneficial thing. And at that point, it was suggested that we sign an NDA, and I said, "Oh no, I'm out of here. That's not going to happen." And so we categorically stated that was a no-go, and I argued that we liked being free to talk about anything we research. It meant we did not have to ask anyone's permission before talking, or to have to act guarded when we're in anyone's company. And it was explained that they had NDAs in place, and that prevented the kind of freedoms we enjoy as the MFMP. And it was agreed that we were trying to work out if there was a way we could test the technology without compromising our freedom. So there was mentions about when the time was right, perhaps we could test something and a location that was suitable to them, or come up with some other way that would be suitable. And you know, we'd have to like argue the case of what we brought to the table, and I think I would hope that we've done enough to earn people's trust in that, if we're going to test something, if it works, it works. If it doesn't, it doesn't. And if we have doubts, we're going to say it has doubts, but this is what we saw and this is what's interesting about it. But that, people can have some faith in the credibility of what's being done at the end of the day. And so as an aside here, and I didn't say this in our meeting, but I just want to say it right here now. When we were with et.al in January 2015 as part of Project Fedora, and thank you to all of those that supported that work. It was really a seminal moment in terms of growing understanding within our community. There was a request after we'd been with et.al for 5 days by niche energy representatives that we signed an NDA as a formality, And I said, well, to be honest, I don't really sign anything until I've read it all the way through. And so they said, no, don't. It's just, nothing serious, blah, blah, blah. And so I took the trouble to sit down and for a couple of hours, and it was not very pleasant, a couple of hours sitting there whilst they're pacing about and reading this NDA and thinking about the implications. And it was very fortunate that I read it, because even after explaining how it would affect our work, they still pressed us to sign it, but we refused it. But it essentially, it essentially said we couldn't do Lena anymore unless we were doing it with them. And there is a real risk that you sign something and then you can't even talk about the things that we have found post signing that thing. Because another party has found it too. And so it cannot be risked. I didn't want to put myself in a position where there's a whole roster of things that I want to share with the community and a whole bunch of analysis that points to a certain direction of the way things are going. And then we suddenly can't talk about all those things because the third party have been keeping it to themselves and they intimate the same information that we already know. So an NDA is just a non-starter. And so I think the black box idea, the kind of sharing information that's not at their best edge or that is not affecting their pattern at all or their commercial interests is the way forward. And if that can't be found, then we have to move forward by talking about how it works anyway. If it is EVOs, it's going to work in this way. Now, they have, of course, had difficulties with SARS-CoV-2, and the next time they will really be able to explore the technology, they said, was from October, and this will be in France, and after which they'll have a lot more to share. However, at this point, we did get, I asked about, people are asking about what type of oils were used and so forth. And there was, he said that they use a dielectric silicon oil. And at this point, I was talking about a number of different things, which I'll talk about here. So the first one is, I talked about this the other day on a presentation I gave recently. And I talked about the narrow gap spark chamber between that starts on page 52 of Space Earth Human. And this was the structure that was able to be the main starting point in the 1980s for Alexander Parkhomov to discover what he at that point was calling N radiation, and later established that it was between microns and millimeters by using diffraction gratings. And that this was able to do inverse beta decay, i.e. stimulate beta isotopes to decay. And he has this device. I showed it the other day here. And essentially, you've got two glass plates with a deposited conductor on it with a narrow gap in between and a photographic film. And then you have this case around it so you don't get any radon gas coming in or dust or whatever. But of course, you can get charged particles like muons go through there and so on. But the point being is that this is where I said, look, if we can't be specific, then but you say you are creating EVOs, and one form of EVO is in my view, this N radiation, this cluster condensed cold neutrinos, then you would have to be doing something like Parkhomov was doing. And in his book, he's saying 10 to the 8 volts per meter intensity. And one other person has claimed 10 to the 7 volts per meter intensity. And so at that point, he did say that the 25 kilovolts, which he mentioned earlier, was actually 20 kilovolts per millimeter. Now, if you look at 20 kilovolts per meter, that is 20,000, so that's 10 to the 4. And then per millimeter, that's another 10 to the 4, so that's 10 to the 8. So that is 10 to the 8, 2 times 10 to the 8 volts per meter. So it is in line with this, and that's what you would need effectively for a cold cathode. Now, the question is, do you have that on the whole time? Probably not. And if you go to the link that I shared, the first link that I shared in the presentation there. So this is from the early 1980s. He actually was able to create these spots on the photographic, the X-ray plate. And these are caused by whatever is assisting the initiation of the discharge, which is a spark discharge. The device is called a narrow gap spark chamber camera. So it's another abbreviation for it is spark camera. And the purpose of this is to have your high volts per meter differential there. This allows for when there's something in there, a discharge, the breakdown of that gap. And you know from Shoulder's work that every time you have a spark will be producing exotic vacuum objects, EVOs. So they are essentially the same thing. Now, on the link, the first link that I gave you in the description there, I referred to work that was done by Alexander Shishkin et al. In Dubna in Science City. And he's referring to, and I discussed the fact that you would need high DIDTs with Michael Ergang. And in this paper, he's saying that he discovered string vortex soliton, which are the sort of black EVOs, the sort of that can pass through matter. They actually do a high voltage pulse of plus or minus 590 volts on an X-ray film in an opaque package located between the plates of a flat capacitor with an 8mm distance. So they've actually got 590 volts plus and minus across an 8mm gap, but it's a pulse. So you've got a very, very high DIDT. And this is not too far removed from the kind of voltage that is said in the patent. And except that it's not DC on all the time, it's a DC pulse. The gap obviously in a device like this would be a lot smaller than 8mm. And we know that because the diameter of the actual tube is 8mm. I did raise a point that in the patent, it says that this device has a 2.3, I think it was, or 2 point something cc vacuum capacitor. And I can't work out how that is. It's 2.25 millimeters long, the main part of the chamber, and only 8mm across on the outside. It's no more than 1.4 cc's inside and less than 1, I should imagine. And maybe that's a typo. But anyway, the point is maybe it was meant to be 1.2 or something, which is very close to what it is, rather than 2.2. But anyway, that would only kind of like make the capacity that it's claiming higher rather than lower. So it would make a conservative estimate. It certainly wouldn't be the first pattern that I've seen an error in on something like that. And like he says, that is not the important part of the pattern. The important part of the pattern is the functional arrangement of the anode cathode in both the and insulator and vacuum in the vacuum capacitor arrangement. But anyway, the point is that Shishkin work proved that you can produce these structures that have these birdies and produce these ions. So they're having many of the properties of EVOs in the black form. So just to reiterate then, Parkhomov is describing in the 1980s this device that got him on the road to understanding this technology. And this was effectively naturally using these structures in the environment, but he later found that you could technologically produce them by having a temperature over 1,000 degrees. Now, so you have, it would seem, two options. You have a thermal emission of electrons, and you have the lower voltage, but ideally pulsed, to have a wave function that's energy wave discontinuity that's more likely to produce EVOs, or you have the much higher voltage without the thermionic emission to create the breakdown and the spark and so on. But still, I would imagine that is pulsed. And so I'm going to give you a whole load of data points that will add up to understanding why this would be the case. So he did suggest that prior to kind of like going into that 20 kilovolts per millimeter, he suggested that there's another approach here for the community, and that is to just like sit back, relax, and wait a year or so, presumably from October. And they will have prototypes that are more predictable, and actually ultimately they will have to have well-specified device data sheets that the end user could consider for applications in their field. So, you know, now, again, I think it's relevant at this point to talk about the reality of the charged nature. In the Lyon reactor, you had a quartz tube, which is effectively, you know, let's say it's the same as this material here, a quartz tube. And inside there, you had something that, from all the evidence, is creating a range of EVOs. And what happened was, it's coming out of the tube in the center, where the diamond and the deuterium and the nickel is. Let's say the EVOs are being made. They're going through the alumina or mullite tube, and then they're getting trapped in the metal of the copper windings that Lyon had put around the central tube. And beyond that, there was the quartz liner. So what happened in Lyon experiment, he took a 20, I meant to bring it with me, but I haven't got it here. But anyway, is a 20-watt halogen light bulb, which he turned off the reactor and so on. And then he touched the metal bolt that it helps to block the end of the reactor, but is also connected to the copper wire. And it apparently, according to him, it lit the light bulb for about 30 minutes, which is quite a lot of power. And this is coming out effectively. He had some sort of sink, some sort of drain or source, whatever, but for allowing the flux of power from this metal, that we can see that there were strange radiation tracks in there. We saw that, an influence of the vortices and the solitons that were shown on the X-rays after it was pulled out and put in with X-rays. So we know that it was a very active structure, even with the power turned off, but that there was something stored in that copper that was able to keep that light bulb running 20 watts, running for 30 minutes. And inspired by that, when I went to visit Suhouse Ralkar later that year, he had one of the demonstrations we were doing. We shared a lot of videos from this, and in fact, this what I'm telling you now is actually published in Infinite Energy in 2017. But I had this idea to. He's doing discharges. It's 2,000 and something volts. I think 2,200, 2,400 volts. It's about 20 kilohertz, 19.46 kilohertz. Discharging with a 200 and something bias. You need the bias to get whatever's produced to drift towards the anode. So it's coming from the cathode and it's going through water. So this is actually very similar to the work of Bogdanovich at the Moscow Physics Institute, where they saw all these toroidal clusters and these crystal forms of toroidal clusters grouping together. So very similar to that, but it was onto a steel rebar, and I've shared a lot of videos about that. But we have a whole series of videos for an experiment, and like I say, the text and the information from this was published in Infinite Energy at the end of 2017. But I really think I need to find the time to put together the package of that experiment, because what happened was, the water drains away almost instantly when you turn the apparatus off, and it sits on two nylon sort of O-rings, And so it's kind of suspended there. And at that point, we had a voltmeter, and we connected it to ground, and we connected it to the rebar, and it read 1.3 volts for a period of time, and then kind of like faded away. Now, one could say it acts as an antenna, and maybe it does, but it's like 1.3 volts. Anyway, we will share that. But the idea was there any voltage that could be observed in this metal, knowing that it's like the Bogdanovich work, knowing what had been observed by Lyon, and could we see anything? And like I say, it's all there on the video. You can speculate about whether there's some chemical effect going on, or there's some sort of RF tuning effect going on, or whatever. But Suhouse was not aware of what I wanted to do, and so there was no real way that he could prepare for this. It was just let's do this, it's doing it, and then we're doing it now, let's put the multimeter on there. Okay. So in fact, I had a supercapacitor ready to charge up to see what level of charge we could get from that, but for whatever reason we couldn't get that operating that time. In fact, we intended to do it, but the ultrasonics needed to be used for a demonstration later in that day, and there wasn't enough time in the day to do it. But we have a number of data points here where charge seemed to be stored by systems that are known to create exotic vacuum objects. And so, and this charge is stored in the metals. And the concept of the vacuum capacitor is that the EVOs don't get to go anywhere. They kind of get stuck, cluster, and then you use the cathode as your source for the discharge. So they're effectively able to be captured by the cathode and drawn off. And so, you know, there are data points that points to this being there. And so I suggested that, you know, in high DIDT based and high frequency, high voltage devices, you could have a situation where you have like a pulse, which is at, you know, you have a permanent bias on there of a few hundred volts, but then you have a high frequency, high voltage pulses on there as well. And obviously this is a lot more complicated than what people initially saw, but I think you're going to have either a larger configuration, a cold cathode, and a very high voltage per millimeter, as defined by Alexander Parkhomov for creating these things, or by Alexander Shishkin, or pulses in a situation where you may have a thermionic emission, but the voltage may be lower. So, you know, and Shoulders did say EVOs can store their energy in the metals. So essentially you're asking to remove the steady state and look to transient states and so on. So when I had said that, he did admit that the pulsed application is one of the voltage approaches that they used, and that's essentially it. So I think what we've got out of this, there's a couple of other things that were mentioned. That use of epoxy resin to isolate the non-used terminals, which, depending on your device, your cathode or your other device, would be larger or smaller number of terminals you would have to isolate. He did say that there was some sort of 1C or something diode that they used, and you can see the picture of that on their website, and that's the one that produced the higher power, and that really they wouldn't recommend using this as a point for replication. However, I had a chance to speak to John Hutchison earlier this evening, and he said that when he was a kid, well, firstly, he said he's got a huge experience in vacuum tubes of all kinds of types, and he recommended the 5U4 voltage rectifier. If you go and search for that, you'll immediately find many versions of that and equivalents of it with various parameters, and the OA3 voltage regulator, and also possibly a 608 triode. And the funny thing was, he said that when he was a kid, I mean, a young child, he experimented with these things. And you know what? This week, I said I was going to be focusing on the magnetic nature, magnetic aspects that you can use and utilize with this technology. And the fact that the exotic vacuum object, certainly Keith Fredericks was able to guide exotic vacuum objects produced from his fingers on X-ray film and film using neodymium magnet. I would appear to have been able to guide them using magnets in the observation of echo fuel, guiding them towards or through rather a piece of plastic as a witness material. And Baranov and Zatelepin, principally Baranov, has been able to use a torsion balance, and I'm going to talk about that in more detail this week, where he has magnets, neodymium magnets on the four corners, and that the radiation coming out of the nickel hydrogen reactor is able to cause a torsional rotation. So it's transferring its they have a magnetic moment that's causing it to stick onto the nickel plate, and they have a torsional moment, and that's causing the spin of the torsional balance. And so he was able to do that. And it's I love John Hutchison, his honesty, his wealth of experience in things that people would never consider of doing. Just came to light here. He said he used to use these old big diodes, and as I say, if you've just missed it, he recommended using a 5U 4 voltage rectifier or similar, an OA3 voltage regulator, or a 608 triode as the basis for it. And then in the case of the first two, you would isolate I think they're both thermionic emission devices, but they're much bigger of the type of device that was used in the more successful work of Freel.tech's patent inventor. And he said, if you bring a magnet close to one of these triodes, it starts sparking. Now, what do we know? We know that Alexander Parkhomov discovered N radiation by using a 10 to the 8 volts per meter narrow gap spark chamber, and then modifying that with a diffraction grating to understand the scale of the radiation that's produced. Then he discovered in work that if you raise the temperature of solid material above 1000 degrees centigrade, you start to produce this same kind of radiation technologically. And what do you have in a thermionic emitter? Well, you have something that could potentially get to over 1000 degrees centigrade. And so this would produce the radiation, but you want to get something that's able to spark. We're saying that this type of radiation can be magnetically influenced, so that if you had your magnet in a particular direction, it would kind of align all of these structures up. And we know that the cold neutrinos can interact with electrons, and they can hand off energy. So you could get a situation where they're magnetic, electrons have a magnetic moment, it aligns up a streamer and helps to initiate a spark. And so, but he just didn't stop there. He said, don't use magnets that are too strong, because if you use magnets that are too strong, it starts pulling the electrodes off if they are iron. And actually, typically, they are actually iron in these things. So you can end up ripping the electrode off in one direction. So I suggested maybe... I've forgotten it now. Samarium cobalt, because that's the highest Curie temperature of any magnet, and it's pretty strong anyway. He said, well, yes, that would be a good one, but also it doesn't need to be so strong. You just need to bring it, and you get the sparking. So, and then he talked about, we had a whole discussion about how to listen for when things are getting into the right situation, because there might be sparks going on in there that you cannot see, and they're at a level that's a little bit below any visual appearance, but that could still be producing exotic vacuum objects. And so he described that he used a AM radio, and he likes to refer to things as megacycles rather than megahertz, and I think it's quite cool, so let's call it megacycles. And he said that he likes to listen, and he says that a particularly good frequency to use is 2.336 megacycles. Now, I don't know whether one can, I'm not being a radio expert, I don't know whether you can get these things off the shelf at that level, but if you can, and it's a standard old AM radio, then great. Let's find out. But again, if you're listening on that, you would hear, I guess, some sort of cracks, pops, or whistles in the white noise. The subject of the first sort of 50 pages of this book is white noise. And so white noise, he describes in this book about how you have, I must go very soon, so give me a sec. I don't. Okay. So I'm going to have to go. So basically, I've said it all. If there are any questions, then please put them in the description of this video, or the questions to this video when it's posted. But essentially, that's it. I have talked about this, and you can go and look at the way that was produced, Alexander Shishkin was able to produce string vortex solitons, which are, in my view, a form of EVO. And I think between those two data sets, the data set of being able to store power in the Lyon reactor, copper, and in the steel rebar of Suhouse rail car, you have the parameter space that you need. It's defined as 10 to the 8 volts per meter in a narrow gap spark chamber, or 10 to the 7 volts per meter, I think, with Shishkin's work. But anyway, you have and you have the materials there, and I've given you link specifications for the 5U4 voltage rectifier, OA3 voltage regulator, and the 608 triode, and how you can potentially listen to these things. So that's it. Thank you. I need to go. Thanks, Corky. Thanks, Steve. Thanks, Alex. Thanks, Chris, Scott, and Artifact. Like I say, any questions, put them down there. I think I've been through everything. Net result is I've essentially said how these things, the type of radiation has been produced. I've given you a wonderful tip today that no one's mentioned before, but tunes with all the other data we have now, is that you can use a magnet to help stimulate the production of these. I guess you would need it in the orientation between the cathode. So if your sheath, which was your anode, was going on the outside, you would want that to be non-magnetic, like stainless steel, or you'd want it to be aluminium and be able to survive the power output from the thermal cathode emission without breaking the glass. So you would want it over there, and so that the magnetic field was able to go through. And I guess you would want the north or the south pole, whatever it needs to be, in line with the emission from the thermionic emission of the cathode. And then pulses, high frequency, or high volts per meter. And that's about it. So thank you very much. I will see you in the next video. And like I say, this week's going to be about a little bit more about magnetics and shielding and torsion balances and so forth. So thank you very much for your time. I'll see you in the next video.